All right, I'll start. So, hi everyone. I'm going to talk briefly on zk-SNARKs and sort of the mathematical foundations of it. We'll sort of start by talking about what zk-SNARKs are and sort of how they work. And then we'll talk about sort of focus on the mathematical underpinnings of them. So things like polynomial properties, homomorphic encryption, knowledge of exponent assumption, cryptographic pairings, and so on. And there's lots of sort of great explainers out there, and this is largely based on previous work, especially one called Why and How zk-SNARKs Works by Max and Petkus, and also great explainers by Vitalik and Gabison that I definitely recommend people check out if they want to learn more. And we'll focus on sort of the key mathematical tools and insights and less on sort of mechanical aspects. So first of all, zk-SNARKs stands for, like I'm sure most of you are familiar, but I'll be brief here, but it stands for zero knowledge, succinct, non-interactive arguments of knowledge. We'll break that down as we go. But essentially, it allows us to prove something without revealing any other information other than that it's true. But first of all, like what are they useful for? So it allows us to do many things. So we can do anonymous authorization. So you can prove that you have access to some system without revealing who you are. Use it for anonymous payments, so kind of making digital money fungible, like we saw with Tornado Cash in the previous presentation. You can also use it for outsourcing computation. So in peer-to-peer systems, maybe you have one node that's doing some expensive computation, and then other nodes can verify that. So a great example for sort of building intuition, especially for lay people, is this game of Where's Waldo that some of you might be familiar with. Essentially, you have this sort of map, and it's kind of messy, a lot of things going on, and you're trying to find where Waldo is. So Waldo is this guy with the red and white striped shirt and a hat. And in this illustration, and in zk-SNARKs in general, like Prover Peggy wants to prove to verify Victor that they know where Waldo is without revealing where he actually is. So you can imagine that you sort of have this Waldo map. It's like a postcard, and then you take sort of a bigger piece of paper, like a cardboard, for example, and you sort of put it in front of this postcard. And then you make a tiny hole in the big piece of paper, and then you position the sort of the postcard with Waldo, so only Waldo himself is visible. And then the verified Victor can sort of see that you indeed know where Waldo is because you can see Waldo, but he doesn't actually know where on the postcard Waldo is. Obviously, this is just like a toy example to build intuition, and it doesn't tell us anything about the actual math behind it, which is what we'll dive into over this presentation. So first off, some sort of protocol properties. So completeness. So if a statement is true, then the prover can convince a verifier of it. And then soundness. So a malicious prover can't convince a verifier of a false statement. And then finally, zero knowledge, where proof only sort of reveals if a statement is true and nothing else. And as it turns out, even though sort of the zero knowledge property seems like the most magical one, and in some sense it is, it kind of falls naturally from the sort of verifiable computing soundness aspect. Oops. So you might have heard that we sort of use polynomials in zk-SNARKs, but why is that? So there's an example polynomial of degree 2, and sort of the more general form here. And it turns out like polynomials essentially have some very nice properties. So to sort of show this, we're going to like have a kind of a straw man simple proof here where I think it's not updating. Is it? Hold on. Oh, anyway, imagine you have sort of a bit array of 10 elements, and then prover Peggy, they want to sort of prove that all entries in this array are set to 1. And then verifier Victor, in order to sort of check this, they have to verify each entry one by one, either sequentially or randomly or something. And so to get 95% confidence, they would essentially have to check all entries. So this is obviously very inefficient. And just looking at polynomials, so you have this fundamental theorem of algebra, which says that the polynomial has at most d solutions. So we have an example polynomial here. You can see it has solutions at x equals 1, 2, and 3. And it's of degree 3. And if you change sort of polynomial a tiny bit, we get a completely different solution. And if you sort of set two polynomials equal to each other, you get another polynomial. So two different polynomials to intersect at most d points. So let's say we want to, Peggy, they want to prove that they know a polynomial and they want to prove this. In this case, let's also assume that the Victor, the verifier, also knows this polynomial. So we have this very simple protocol where Victor, the verifier, is sort of choosing a random value for x, so say 7, and then evaluates this polynomial at that point, which gives us 120. And then it gives sort of this random value to Peggy. And Peggy also evaluates p of x locally and gives the result back to Victor, so 120. And if the results are the same, which they are in this case, 120, it's very likely that Peggy sort of knows the same polynomial as Victor. And to see why that's the case, you can sort of imagine that you have a range of x values that's from 1 to 2 to the 252nd power. And so the probability that Peggy would accidentally pick a point where the evaluation of the polynomial would be the same is the degree of the polynomial divided by 2 to 252, which is very unlikely. So polynomials are very sort of easy to work with when it comes to operations like addition and multiplication and so on. And hopefully this gives us some illustration of why zk-SNARKs rely on polynomials in terms of sort of contrasting with the naive proof we saw initially. But it's also likely that there are other forms of proof mediums that exist. So in a better world where Peggy was trying to prove that they know p of x, in a better world, Victor wouldn't actually know p of x on its own, only Peggy would. And then Peggy would prove that they know this polynomial. And because of fundamental theorem of algebra, you can sort of factor polynomial into a product of linear factors. So we can express p of x as such. So you have these factors that correspond to the solution. So x minus 1 times x minus 2 times x minus 3. And then instead of Victor sort of knowing this polynomial p of x, it would know a target polynomial called t of x, which are sort of cofactors in p of x. So in this case, say t of x is x minus 1 and x minus 2. And then p of x is essentially just a multiplication of t of x and then some arbitrary polynomial, which we call h of x, which in this case is the factor x minus 3. So in this sort of slightly modified example, instead you would have Victor. They would evaluate sort of the target polynomial at the random point r, and then give this r to Peggy. And then Peggy would calculate the arbitrary polynomial, and then also evaluate sort of polynomial at point r and sort of the arbitrary polynomial at point h, and they would get sort of these p and h evaluated numbers, and then give them to Victor, the verifier. Who would then check that sort of this verification check, this consistency holds up, so that p is equal to t times h, which what that means is essentially that t of x is a cofactor to p of x. So in the previous example, Peggy knows the value r that Victor chose, and it's kind of a problem because it means that Peggy might not actually know p of x at all. So Peggy can instead cheat, and it can choose a random number h, and so set the polynomial to p equals t, the target polynomial evaluated at r times this random number h, and then the sort of Victor would accept this because the verification consistency check would pass, despite, and this is the case despite that Peggy doesn't know p of x, so it kind of breaks soundness. So what we're going to do is we essentially want to hide r and t of r from Peggy, so they can't cheat and break this soundness property. And this leads to this concept of homomorphic encryption, where the idea is that we encrypt some number x with some function e of x, so it's harder to find out what x is. And different inputs, they have different outputs. And if we know sort of the encrypted value of x and y, then we can compute sort of basic arithmetic expressions, such as sort of addition. And you can kind of think of this like hash, but with basic math functions. And under certain assumptions, we can think of the modular operation as a form of encryption. So let's see why. So as a starting point, imagine we sort of choose a base g, and then we encrypt the number by exponentiating g to it. So for example, we have a base 5, and then we want to encrypt the value 3. 5 5 to the power of 3 is 125. Then it's kind of, in this case, it's very trivial to find the number. You just divide by 5 until you get 1, and the number of steps is the encrypted value. So that's not very useful. But if you use modular arithmetic, it's kind of over a finite field. So it's a subset of all natural numbers. And it's essentially like clock arithmetic. So it's a 3 o'clock, and then plus 12 hours is the same. It's 3 o'clock again. So we have this sort of new encryption function where to encrypt the value is the same as taking this g to the power of v mod n. So that's kind of neat with this is that you have different values. They end up with the same results. So it's hard to figure out what the encrypted value is, especially if the order, what you're taking modulo of, is high enough. This is called the discrete logarithm problem, and essentially says that if we choose this base g and order n right, then it's very hard to figure out what v is in this expression. In this case, we're using this group, so the multiplicative group of integers modulo p, where p is a prime number. And a group here is just some set of operations, some set of elements, integers up to p minus 1 in this case, and some operation, multiplication in this case. And since p is a prime, it's what's called a cyclic group. And that means that there's a generator, and you have a generator that can sort of generate every element. So you can sort of, with this generator, you can get every element in this group. And you also have equivalent groups that exist for elliptic curve cryptography, which we'll touch on later. So now we have a way to compute sort of the x plus y encrypted from the encrypted values separately. But we can't exponentiate encrypted values yet, which is what we'll look at next. And we also can't multiply two encrypted values, which leads to the concept of cryptographic pairings, which we'll touch on later. And this is a very basic form of homomorphic encryption, and with something called homomorphic encryption, we can sort of do arbitrary computation on encrypted values, which is like a separate field. All right, so we can't exponentiate encrypted values. So instead, what we do is we essentially encrypt polynomial by doing each power separately. And if you think about it, to know a polynomial is really, you know its coefficients and its degrees. So in this case, we have this polynomial. The coefficients are 1, minus 3, and 2, and has degree 3. So what we do is we encrypt each of these terms. So x to the power of 1, x to the power of 2, x cubed, and then we encrypt these powers. And then the prover is sort of given these encrypted values. So we have all these encrypted powers, and when you apply this encryption function with the coefficients and sort of add them together, the result is that our polynomial is encrypted at some x. So with that, how does that change our proof procedure? So as before, you sample some random value. Here we call it s. And then we encrypt s for each of these terms, each power. Evaluate the unencrypted target polynomial at t of s, so the target polynomial at this secret point s. And then we provide these encrypted powers to prover Peggy. So similar to before, so Peggy calculates this arbitrary polynomial h of x, and it's using these encrypted powers that was given by Victor, and applies the sort of coefficient for the p of x polynomial. And then we do the same thing for the arbitrary polynomial h of s. And then we provide these sort of p and h values like we did before, but this time in sort of encrypted space. So now Victor is checking that p is equal to target polynomial evaluated at s times h in encrypted space. So that means that t of x is a cofactor of p of x. And it's kind of progress, right? Because now Peggy doesn't know s or the target polynomial evaluated s, but it can sort of use the encrypted evaluation. But we have a problem because it's still possible for Peggy to sort of not use these encrypted powers as intended. So in zk-SNARKs, we can sort of think of the coefficients as representing knowledge. But for that to be sort of the case, we have a requirement. We need the proof to be based on the exponentiation of these encrypted powers. So a polynomial has to be on the right form. And if it isn't, then Peggy can essentially cheat, breaking soundness. So as an example, Peggy can use some random r, set h to g to the power of r, and then set the p to the expression there. And then the verification check sort of checks out, despite Peggy not knowing p of x, which breaks soundness. So cheating is possible here because Peggy can sort of exponentiate to some value other than s. And what we're going to do is we want to ensure that we always use the encrypted powers of s that's provided to us, and only sort of add coefficients to it. And this can be done with something called the knowledge of exponent assumption. And the basic idea is essentially that Victor, the verifier, is choosing some random alpha, and then he calculates alpha prime, which is a to the power of alpha, mod n. And then he provides this tuple a and a prime to Peggy, who then has to sort of take each element and exponent in this tuple and exponentate them to a random value, and reply with the corresponding tuple b and b prime. And here, as we saw before, Peggy can't sort of reasonably extract alpha from a prime. So it's kind of a secret parameter. And the assumption in this KEA is that the only way for Peggy to produce this valid b prime tuple is the following. So choose some random c, and then calculate b and b prime by taking a and a prime respectively, exponentiating it to c, and then replying with the b prime tuple. And then Victor sort of verifies that this holds with some variable substitution, and you'll see that it's the same expression, and the exponent c must be the same. And this kind of alpha shift, this is a useful tool in terms of restricting polynomials and sort of maintaining the invariant that we only applying coefficients to the encrypted powers of s. So sort of g to the power of the coefficient times s for each term. And if you have polynomials with multiple terms, you essentially do the same thing, and then you use homomorphic encryption to add them together. And this adds one more called like a polynomial restriction verification check for the verifier. So previously, Peggy was providing g to the power of p and g to the power of h to Victor, but now it's also providing this g to the power of p prime. So Victor can check that the polynomial is on the right form. Cool. So with this, we have what's called a computationally sound protocol. So essentially, a prover can't convince a verifier of a false statement, and we call it computational because it's still it's called small, like a soundness error, but it's kind of an arbitrarily small possibility that Peggy can provide a false proof. But we can be very rigorous about this soundness error, sort of quantifying it and minimizing it. So in practice, it's not something we worry about. But it's still not zero knowledge. Because for it to be zero knowledge, we don't want to leak anything about the original polynomial p of x to Victor. So Peggy just wants to prove that they noticed the polynomial. They don't want to leak anything about what the polynomial actually is. Let's look at the state of things right now. So if p of x is simple, so let's say the coefficients are range from 0 to 10, and then degree 2 or something, then it's very trivial to brute force and find out p of x. And what we want is kind of a secure protocol that's regardless of the number of coefficients or values. And if we recall the actual verification checks that Victor the verifier is performing, it's checking that p of x has the target polynomial as roots in this encrypted space, and also checking the polynomial restriction. So what we saw before with the alpha shift, making sure the polynomial is in the right form. And we're going to do essentially use the same idea as we did with alpha shift, where essentially Peggy is choosing a random delta and then exponentiating sort of her proof values to it. And that's kind of introducing some randomness. And the verification check, they still hold, but p of x can't easily be brute forced with this additional term. So one pretty neat thing here is that once we had sorted out soundness, then we got zero knowledge for free, essentially. So that's neat. But so far, the proof is still interactive. So non-interactivity. So this is the N in zk-SNARKs, and sometimes it's called non-interactive zero knowledge. So the current state is that a proof is only valid once, and then if some other verifier wants to verify, they have to start over. And Victor can kind of cheat and share their secret parameters with Peggy or something. This leads to this sort of idea of publicly verifiable proofs, that you only prove something once, and then anyone can verify it after. And this is especially attractive with public blockchains like Ethereum, because you can sort of write the proof once and have it to the chain, and then other people can verify it whenever they want to. So the general idea is essentially that we want to keep the secret parameters public, secure, and reusable. And we add a setup phase before where we sort of compute the target polynomial evaluated at S, secret, and then alpha to sort of compute them securely. So you might think, well, before, didn't we have this homomorphic encryption? Can't we use that? The problem is that we can't multiply encrypted values, which is necessary for the verification check. So you see here that the secret stays sort of as a multiplication term, so that doesn't work. So that leads us to the concept of cryptographic pairings. But first, let's talk briefly about elliptic curve cryptography. So, elliptic curve cryptography. It's used for public key cryptography, and it essentially allows for smaller keys with similar security RSA. So, a 256-bit ECC key corresponds to a 3072-bit RSA key. So it has a 10x impact on performance, which is why a lot of products are using them now. And previously we had sort of, well, it's based on elliptic curves over a finite field, where there's sort of, you have these points A and B that's satisfying this equation, as well as it's called a point of infinity, which is kind of like 0 in normal arithmetic, so kind of additive identity. And earlier we sort of had this multiplicative group of integers modulo some prime, or sort of over some finite field modulo p more generally. And we have a kind of similar discrete logarithm problem for elliptic curves over a finite field. And sometimes it's called sort of the elliptic curve discrete logarithm problem, ECDLP. And sort of how to choose these curves and making them pairing friendly and so on is a whole thing, or field of its own, or subfield. And if you're interested in that, I recommend checking out DGB's Daniel Bernstein's work on safe curves as a starting point. So cryptographic pairings. Pairing-based cryptography is used a lot in modern cryptography. It allows us to multiply encrypted values using bilinear maps. It's kind of it's a mapping between these two cyclic groups and then some other group, GFT. And this output group is kind of in a different space. In our case, what we care about is mapping of elliptic curves over finite fields. So if you read this sort of equality, you can sort of think of it as very sloppily that you just focus on the exponent and you sort of swap place of the exponents. So in this case, we see AB is equal to BA. E should also be efficient to compute and non-degenerate. So a kind of illustration of this, output group is in a different space, and we can't sort of take the output and use it as input in another pairing. So we're kind of teleporting ourselves into a different dimension, and sort of unlike Rick and Morty, we can't just easily go back. And finding pairing-friendly curves here is a bit of a problem, where we kind of want to balance the E being efficient to compute with the discrete logarithm problem being hard in the output group. So as a brief aside, the first sort of cryptographic pairing was defined by Andrew Weil, who was part of the Bourbaki group. And he defined it when he was in jail during World War II, and he had pen and paper, and he was very productive. And he suggested mathematicians go to jail in order to be productive. So maybe COVID restrictions aren't so bad after all. So a very basic example of pairings is in BLS signatures. It's kind of elegant as well. So BLS signatures are very short signatures that allow for aggregation. So you can have multiple parties that are signing some result, and it results in one signature, and it's used in Ethereum too. And essentially, so you have this key generation function where you have some secret, like private key kind of, and then you take G, that's like a generator to the power of alpha to get the public key. And to sign a message, you take the hash of the message and then exponentiate it to your private key, your secret key. And to verify it, you sort of check this pairing equality. And if you remember, you can sort of basically, if you do the variable substitution here with the public key and sigma, the signature, you can essentially sort of swap the place of alpha. So in the web 2, we have the left side, the right term in the left side, you have an alpha exponent, and then on the right term, left side, where you have sigma, you get an alpha exponent. And so both sides equal to the same thing. So if the signature is valid, it's all good. And you can sort of think of the output as a new generator, G2, that allows us to add encrypted products of multiple pairings. And as a kind of an aside, so this is like we had looked at bilinear maps, but this is concept of multilinear maps, which is a very hard sort of research problem. So in this case, just having a free linear map is hard. And if you solve it, then famous cryptographer Dan Bonnet will be your friend for life. There's that. Right, so with this cryptographic pairing, essentially we can do a trusted setup. So the idea is that you have a setup phase before you do proving and verification. And as a kind of starting point, we can assume that we trust a single entity. And then the proof is done once and then can be verified many times after. And we have this concept of a common reference string where all of these secrets, we generate the secrets S and alpha, as well as the encrypted powers of S with this alpha shift. And then once we are done, we sort of delete the raw values. And sometimes this is called toxic waste. And it's called that way because it's waste. You don't need it anymore. And it's toxic because if you get a hold of it, then you can create fake proofs and stuff. So how does it work with cryptographic pairings? So you have this common reference string. You generate these parameters, and we can split it up into two parts. You have sort of a proving key part and then a verification key part. And essentially, you do the verification check as before, but now with pairings. So we're essentially still checking that P is equal to T times H in encrypted space, so that T of X is a cofactor of the polynomial that Peg is proving that they know. And if you sort of squint and just focus on exponents, you'll see that it holds. And then we do sort of the same sort of pairing consistency check for polynomial restrictions, so making sure that it's on the right form, like we saw with the alpha shift and knowledge of exponent assumption earlier. So we can extend this to trusting one out of M parties with a composite common reference string. And it's very sort of similar to some tools I use to do this. There's some things you have to be careful of. So you have to be careful that you're sort of doing it sequentially, where the output of one step is used as input to the next one. Making sure that each step is used, as well as some additional checks to make sure there's sort of no toxic waste is leaked. Also, sometimes it's called a ceremony, and it's sort of elaborated on in the study of multi-party computation. And you can join one yourself and participate. For example, there's the perpetual powers of tau, as well as others. So if you don't trust other people, maybe you trust yourself, and then you can be part of this ceremony. So looking sort of beyond polynomials, so far we've been focused on proving that Peg has been proving that they know a polynomial. But how do we actually use it for computation? So the idea in brief is that we convert some computer program into math formula, and then we sort of turn this into a set of simple constraints. And then we express these constraints as a polynomial relationship between polynomials. And then we find a polynomial that represents these constraints. So Peg is essentially proving that they know the result of some secret computation, and then Victor checks that the constraints hold. So the goal in the first step is sort of you're converting a program into some set of constraints. You can use variables and constants and binary operations. So for example, let's say you have a function with some binary argument w, it's a binary number. Then we might have the following constraint. So 1 times w times 1 times w equals 1 times w, which is only valid for w is 0 or w is 1. So it's a binary number. And essentially, we can get these called arithmetic circuits. And it's kind of similar to making a computer with logical gates. So you start with a NAND gate, and then eventually you get Minecraft. So if you have multiple constraints, you can sort of chain them together with intermediate variables. So here you have a times b equals r1, and then r1 is used in the following constraint. And if you have some more concrete example, you have multiplication of these numbers, then it takes 3 constraints to sort of express that. So you have 2 times 1, you get output 2, and then use that as input. So 2 times 3 is 6, and then 6 times 2 is 12. And in the real world, sort of you have a lot of constraints that have to hold at the same time. So we saw in the previous presentation, there were a lot of, I forgot exactly how many, but yeah, it's a lot of constraints that have to hold at the same time. And this type of constraint system is called a rank 1 constraint system. And rank 1 is referring to the resulting matrix if we use a kind of linear algebra representation. So we want to express the constraints as what's called a operational polynomial, which is this equation here. So you have some left and right operand polynomial and some binary operation, and then you get an output polynomial. And at some x equals a, the corresponding value in the constraint represents the evaluation of that polynomial, so L of x, and similarly for R of x and O of x. So a more concrete example here. So going back to the previous numerical example, we have a sort of a left operand operation, right operand, and output. And we can look at these constraints as kind of rows. So the first row has 2 in the left position. Second row also has 2, and the third row has 6. And we're essentially looking for a polynomial L that represents the left operand at each row. So for example, here L of 1 is 2 because the first row has the value 2 in the left position. And we do this for sort of each row, and then this gives us 3 points. And these are the 3 points that the polynomial that we're looking for must go through. So we have some set of points, then we want the polynomial. What do? We do polynomial interpolation, and allows us to, so all polynomials can be expressed in this general form, and we use interpolation to find the sort of A, B, and C that goes through these points. In this example, it's a sort of very basic set of equations with some unknowns. If you remember the fundamental theorem of algebra, in this case, we have sort of n plus 1 points, so 3. That means that there exists a polynomial of at most n, so 2 in this case, degrees that polynomial exists that expresses this. And then we solve for A, B, and C, and we get sort of the operand polynomial, which is what's there? L of x equals 2 times x to the power 2 minus 6x plus 6. In practice, because we have a lot of constraints and sort of speed and performance matters, we might use Lagrange polynomials, or even better, sort of fast Fourier transforms. And then also in practice, it's a bit more involved. There's some gotchas. It's largely mechanical, but you need to take care of variables and constants and so on. And basic idea is essentially the same. And polynomials are very flexible, so you can sort of scale them and compose them and so on. And what we did for the left operand polynomial, we do for the right operand polynomial as well as the output polynomial. So one thing that's pretty neat is that no matter how many constraints we have, we sort of end up with a single polynomial. And so the final proof, there has a few more polynomials, but essentially we're compressing down a program into some constant form that's independent of the size of the computation. And this is where the term succinctness comes from, so the S in zk-SNARKs. So just briefly on sort of variable polynomials. So polynomial composition means that we can express many additions and constants in a single constraint. So what we do is we sort of split up the operand polynomial into individual variable polynomials. And then we kind of get constants and additions for free. And sort of give you an illustration of this, how you get these free constants and free addition. So here you have this L of x polynomial, the green big line, that's sort of composed of free curves, where a times L of a, LA of x, that polynomial is a at x equals 1, and then 0 at x equals 2 and x equals 3. So it means that we can essentially scale by some constant. And then we can do the same for b and c. And then in order to sort of do addition, we can sort of take the a plus c at x equals 1, take those curves and sort of add them together to basically get this L of x polynomial. So hopefully this gives some intuition for why constants and addition can be expressed in a single constraint. So all of this together, the variable and target polynomials together, they're called a quadratic arithmetic program. Sort of allows us to turn computation into polynomials. So where did we end up? Well, previously, Peggy had to prove that they know a polynomial. And instead they prove that they know the result of some computation. And then Victor is essentially verifying that this constraint holds. And the main difference is that we have to check a few more polynomials, add some verification checks when it comes to variable values and value operations. Also, this is concept of like private and public inputs. So you have some computation, C of x and w, where x is sort of the public input and w is the witness, so that's a private input. And this allows sort of the verifier to supply their own input. So Peggy proves that they know a witness w such that the computation is true. So for example, which we kind of saw in the previous presentation, that so Victor's applying some hash of some secret S, and then Peggy can prove that they have access to S, which hashes to it, without actually revealing the secret S. So we looked at zk-SNARKs, what they are and what they're useful. And then we looked at sort of the mathematical foundations underlying them. We looked at polynomials, why they're used in zk-SNARKs, their properties. We looked at how to prove that we know polynomial, how to hide information with homomorphic encryption. We looked at how we can use knowledge of exponent assumption to sort of ensure soundness. We also saw how we could get zero knowledge for free. Then we looked at how to make things non-interactive as of the shape of a trusted setup. We looked briefly at elliptic curve cryptography and sort of why we need cryptographic pairings and roughly how they work. And then we looked at how sort of to go from computation to constraints to polynomials. And we also looked at sort of how to achieve succinctness by compressing constraints down into polynomial expressions. Yeah, so hopefully this was interesting to you. If you want to learn more, I highly recommend checking out Petrik's Why and How zk-SNARKs, as well as Vitalik's writings on this, and Ariel Gabson for more. Yeah, and zk-SNARKs is just one of many types of zero-knowledge checks. There's others that have different security assumptions. If you need a setup or not, as of what the underlying computational hardness problem is, the discrete log problem or something else, as well as performance, so proof size and time and so on. Yeah, that's it for me. Thank you. Any questions? You can find me here on Twitter and back as well.